points should be temperatures, whether they're Celsius or Kelvin, they're temperatures. The enthalpy of fusion, so you need to know first what is fusion. That's the melting, solid to liquid. And so that is that little tiny flat line at the very beginning there. And the enthalpy of fusion is defined, I mean, it's how much energy is required to melt 1 mole of that substance. And this chart is actually set up in kilojoules per mole, and it starts melting at 0.6, it ends at 2.8. So if you do a subtraction, 2.2 kilojoules per mole is the enthalpy of fusion. You could do the same thing for the enthalpy of vaporization if you wanted. It's a much bigger energy. Okay, and then so for 5, so let's do this. Let me turn the screen on.
Wait, so would the enthalpy of like vaporization be like 0.6 then?
Oh, so well, okay. So it starts at 16. That's where it starts turning into a gas, and it ends at
Oh, so it'd be
51.2, and so you do a subtraction. 51.2 minus 16.
okay. So it's, okay, I get that. Yeah.
And then, I mean, that's the total amount of energy that went into vaporizing it. So it started this and then ended there. That's the total amount, that difference. Okay, so for the Clausius-Clapeyron equation. So I'm just going to do one of the homework problems, which, oh, that's not it. There it is. Somebody kindly presented this to me in an email. So let's start from this, okay? So this is not what you got in your quiz. This is like the very beginning. So if you have this data here, right here, 65 temperature, that's the vapor pressure measured for that liquid. At least this is nitrogen. 70, 80, it keeps going. As you increase the temperature, the vapor pressure goes up. So if I plot that, and let me just plot that. So move this over here, move this over here. Oop. And then I'm just going to do temperature versus vapor pressure. Let me make that a little bigger so you guys can see that. There we go. Okay, now it's getting too big. That's fine. You can barely see the one on the screen there. So 65, 70, 75. No, that's not working. 65, 70, 75, 80, 85. And then my pressure, these are all a torr. It's fine. 289. 570, 1028, and 1718. So if I plot this, you do that, insert a scatter plot, and it doesn't show. Let me shrink it a little bit. There we go. I don't know why the axes are a little weird here, but you can see it curves. It's not linear. It definitely curves. And if I make the, here, let's make this a little bit more reasonable. Size? No, I always forget now. Let's see, properties. There we go. Axis options. You know what? I've forgotten how to use Excel. It's so different now. Axis options. There we go. So minimum, let's make it 50. No. 50. Okay, so now you can see a little better. It definitely curves. Anyway, so that's no good. We can't, it's very difficult to fit curved lines to data like this because it's hard to tell whether it's squared or if it's a quadratic. I mean, not a quadratic. Any other kind of relationship. So instead, we're going to use the Clausius-Clapeyron equation, And the way that looks is, it's right on your quiz. It's rearranged. Natural log of P is equal to minus delta H vaporization over R times 1 over T plus natural log of beta. And so that has the form of y is equal to mx plus b. So instead of plotting plain temperature and pressure, I'm going to plot natural log of pressure and 1 over the temperature. So there's my data. I'm going to do here, I'm just label it 1 over T. And I will just take, so equals 1 divided by this number here. And I'll copy it all the way down. That's that same formula. All right, so now this is all 1 over temperature. And here I'm going to do natural log of vapor pressure. And I think it's at ln. Yeah. And I'm going to do ln of this thing. Okay, they don't use at anymore. Anyway, that works. Copy it down. Okay, so I'm going to delete this graph. And instead, I'm going to plot these two. So this is going to be in my x, that's going to be in my y. Insert scatter plot, just the points. And again, the axes are a little weird, but that's a lot straighter. That's looks like a straight line to me. Let's see if it really is. I'm going to add a trend line. So add trend line. Come on. My right click gets stuck. Linear trend line. We're going to have it show. Where is it? We're going to have it show the equation, display equation on chart. We'll also display our R squared just to see how straight it is. All right. And there it is. I mean, it's tiny. I would probably change the axes, but I don't want to do that now. There's our equation. Minus 711.98x plus 15.833. It's a really good fit. It's 0.9999. The closer it is to 1, the straighter it is. So we got to remember, this is the Clausius-Clapeyron equation. This y is actually natural log of pressure. This x is actually 1 over t. So the slope here is, according to our equation, negative delta h over r. All right, and that's where we'll start going to board. So our slope is equal to negative delta h of vaporization over r. And our slope in this thing is negative 711.98. So this is where the quiz comes in. We have different numbers, but we will be plotting 1 over t on the x-axis. We'll be plotting natural log of the vapor pressure on the y-axis. And it is doing the right way. So negative delta h vaporization over r. R is 8.314. And while I think we told you this. Yeah, we told you the units of the slope. So the slope's units are always going to be Kelvin. In the quiz, we told you what they are. This is joules per mole per Kelvin. And if you ever make a mistake with the algebra, you can use the units to kind of help figure out if you forgot to divide, or how should you do it. So you're going to move this over here. You'll end up multiplying them. And if you see what happens here is equal to negative delta H vaporization. The negatives cancel, right? So that negative goes away with that negative. And we're left with Kelvin that cancels. Kelvin in the numerator, Kelvin in the denominator. And we're left with joules per mole. It's perfect. So in this problem, let's see what the math says. It's 711.98 times 8.314 is 5,000. Yeah, it's pretty low, but that's fine. 5,919 joules per mole. That's typically not the units we use for enthalpy. We usually see it in kilojoules per mole, which I believe the problem asks for here. There it is. So quick conversion. We're going to multiply by something that cancels joules. gives us kilojoules. 1 kilojoule is 1,000 joules. So we end up with 5.9 kilojoules per mole. I rounded it a little bit, but does this make sense? So what does delta H of vaporization mean? It's the amount of energy required to vaporize 1 mole of that substance. Well, what substance are we talking about? This is nitrogen gas. It's already a gas at room temperature. In fact, it only is liquid at super, super cold temperatures. So it would make sense. It doesn't take a whole lot of energy to vaporize nitrogen. Unlike water, which would have a much higher delta H of vaporization. So on the exam, the answer for ammonia's delta H of vaporization was about 24.7 kilojoules per mole. Okay. So again, doing this whole thing, graphing from scratch, that's not something that's easily done in an exam, but you should be able to at least go from here and figure out what you need to calculate. So the other thing we could get is the beta value. So in the other part of the equation, the natural log of beta is equal to the y-intercept, and our y-intercept is 15.833. So how do you get rid of this natural log? You take e to both sides, and this beta then comes out, and it becomes beta is equal to e 15.833, and you plug that into your calculator. It's going to be some really big number. So 15.833. Oh, wrong one. 7.5 times 10 to the 6th, I think. Okay. Any questions about that? I mean, that's the Clausius-Clapeyron equation. It is literally, I mean, in that previous graph, that the original form of the equation, which we don't really use, describes the curve part. But it's hard to fit nonlinear data to that equation. It's better to use linear data. That's kind of the modus. I mean, that's what we do. We try to get a linear fit because it's very easy to gauge whether or not your imperfect data is fitting a linear equation or not. If you've got imperfect data and you're trying to fit a curve, it's hard to tell, is your curve good? I mean, is it right? With a straight line fit, you can tell if your data is really imprecise, full of error or not. This is pretty perfect. You don't normally get perfect data like that. Okay. Yeah, question?
I have a question about paper.
About what?
My paper.
Oh, yeah. Is there someone of yours?
Yeah, actually, did that label right? Isn't it like what the last question was?
Oh God, I missed that. That's okay. I missed it. It's supposed to be the other way around.
Yeah, so I was just confused because I was pretty sure I got that one. Which was that?
I missed it. That's your win. Yeah. Okay. So yeah. Don't ever tell me stuff like that. It's fine. All right. So let's move on. If anybody has any questions about this, no? Okay. I'm sure there's another question we can see. Let's just close it for now. Ooh, okay. So let's try some exam questions. So just to make sure, we've got our molar volume, we've got the Clausius-Clapeyron equation that we are going to use. We've got our speed of the gases, kinetic theory stuff. We've got our Coulomb's law, the van der Waals equation for real gases. You get your mole fraction for partial pressures. PV equals nRT converted into using density. So we've got a lot of stuff there. Notice the two different R's. Knowing when to use them is important, okay? So you'll use one when you know you are using pressure and volume in your equation. You'll use the other when you know you're not supposed to use energy. And if you still can't tell, remember that joules is a kilogram meter squared per second squared. So here, we need joules here in R so that the kilograms cancel out. Remember, that needs to be in kilograms per mole, things like that. All right, we'll go over that when we see those problems. We got electronegativities. There we go. And so let's go from scratch here. So we have these electrostatic forces. What are the from weakest to strongest? And so London dispersion forces is always going to be generally the weakest. After that, ionic is not next. Ionic is probably the strongest of the kind of electrostatic forces. So again, what are electrostatic forces? It's not a word we use often, but it involves charges, attraction between charges. So while ionic bonding is not technically an intermolecular force, it is electrostatic forces. And intermolecular forces operate through electrostatic forces as well. So it looks like this one is it. Dipole comes next, then hydrogen bonding, then ionic. If we had dipole ion, that would go right in between here. But other than that, it's B. So, oh, you have a question, sorry.
I don't know. I'm like it's ionic, and what's the other one? I'm sorry, blanking on the word.
Dipole ion.
No, it's like ionic, and then there's
Covalent.
Thank you. I remember seeing like later in the thing, it's like covalent stronger than ionic, which I got kind of confused by because then there's a lot that are covalent, but then.
So, I think that the strongest ionic can be stronger than covalent. But I think on average, covalent bonds are stronger than ionic bonds. Especially if you've got a covalent network solid, where it's just everything's connected via covalent bonds. So diamond is harder than any ionic solid, even though So it's a little bit harder to compare those, but I think in general we consider covalent bonding to be stronger than ionic bonding.
All right.
On average, yeah. Okay. I think. Well, see, the other thing is with ionic bonding, you can separate the particles and not destroy, not change what they are. They can still be ions. Whereas with covalent bonding, once you separate them, it kind of changes what they are. So it's usually an irreversible change kind of thing. All right. So which species below would you expect to show the most hydrogen bonding? So this is a tough one because it's true that HF has the strongest hydrogen bonding because HF is the strongest dipole moment for one bond. But 2 OH bonds is going to make do stronger hydrogen bonding than 1 HF bond. And while there's 3 NH bonds, the NH bond is substantially weaker than the OH bond. So the H2O is going to be the strongest in this case. And one way to kind of verify that is just look at boiling points. Water has a higher boiling point than ammonia does. So that just shows that water has stronger IMFs than NH3. So water has the most hydrogen bonding. The OH bond by itself is kind of the middle of the road dipole moment. But 2 of those is stronger than 3 NHs, and it's stronger than 1 HF. Okay. So H2O. The formatting is a little weird in this one. But we have these compounds from group 5A with hydrogen, and they make these different compounds with different boiling points. The first 3 elements illustrate a trend where the boiling point increases, the mass decreases. However, ammonia does not follow the trend because
Hydrogen
hydrogen bonding. All right. So, sounds complicated, but it's simple in the end. It goes back, so they all go down as you get smaller, and then it goes back up when you get to nitrogen. What types of intermolecular forces exist between HI and H2S? So, HI, I mean, you can draw these out. It's not super necessary. That's HI. Iodine is not the most electronegative element, but you know, you could say it's a little bit electronegative. So there's a small dipole there, like that. It's definitely not symmetric, so it's not like methane is. So it's got a small dipole. H2S is bent. If you actually do the Lewis structure for it, it's going to have these two lone pairs. And S is definitely more electronegative than hydrogen is. So they're going to go that way. And then in total, the dipole moment's going to go that way. This is going to be the partial negative side. That's going to be a partial positive side. So that's polar as well. And so we're going to have dipole-dipole interactions between these compounds. No hydrogen bonding. There's no oxygen, no nitrogen, no FH bond. There's no ions there as well. Dipole-dipole. But you got to remember that everything does dispersion forces. So in addition to the dipole-dipole forces, you'll also have dispersion forces. Everything does dispersion forces. So this question is not what's the strongest interaction. This is asking what are all of the interactions. So C, dipole-dipole and dispersion forces. Okay. C12H26 molecules are held together by. So you could draw this out if you want to see, is it an alkane? Is it an alkene? It is definitely an alkane. One of the formulas could help. So it's double the carbons plus 2. So double the carbons is 24 plus 2, 26. It's definitely an alkane. So nothing funny, just all single bonds. So there's only, it's nonpolar, so there's only dispersion forces that hold these, the individual molecules close together in a liquid. So E, dispersion forces, okay? All right. These keep going. So the predominant intermolecular force in this thing. Let's draw it out just to make sure. This is a condensed structural formula. So it kind of is giving you a sense of how things are connected. You've got a CH3 in parentheses 2 next to a nitrogen. That kind of means that there is this CH3 on this nitrogen. There's a CH3 also. And then on the other side of the nitrogen, there's a hydrogen connected to it. So that's what it is. If you want to do a Lewis structure, there's a lone pair on it, but that's not super necessary. But you can see here this NH bond. As soon as you see that NH bond in there, this does hydrogen bonding. So hydrogen bonding is going to be the predominant intermolecular force here. D. All right. Argon has a higher melting point than neon because, well, argon is an atom. Neon is a plain old atom. They don't make any compounds. So there's no polar bond. There's no bonds. There's no polar bonds. These are completely nonpolar. They're neutral. Well, the only thing they have going for them is dispersion forces then. London dispersion forces. And so if argon has a higher melting point, it must have stronger dispersion forces. So C. Why does it have stronger dispersion forces, FYI? Yeah.
Heavier.
Heavier, but
Like,
that's
more
just
mass.
that correlates. Like the heavier things are, generally, yes, they have higher, stronger dispersion forces. But in this particular case, the reason is the electrons in the valence shell are further away from the nucleus. So argon's valence electrons are in shell 3. Neon's valence electrons are in shell 2. Those shell 3 electrons are what we call more polarizable. They are more loosely held, easier to influence, easier to distort. All right, and so the bigger the atom gets, the more polarizable its electrons are going to be. Okay? And that's why we say molecular weight, because the higher the molecular weight, the bigger the atom is going to be. But it's specifically because of those electrons on the outside. Okay, number 8. Based on the molecular mass and the dipole moment of the 5 compounds, which should have the highest boiling point? Any ideas? Acetonitrile, yeah. Yeah, it's hard to say, yeah. So they are relatively similar molecular weights. Yeah, that's a little heavier, but despite this being a little heavier, its dipole moment is not super strong. It's pretty good. That's much higher. So the stronger the dipole moment, that basically means the stronger that partial positive and partial negative are. The larger those partial charges are. Yeah.
So that like overrides if there's like if there's like an OH group or something. Well, I guess.
Well,
OH
so an
minus
OH group, this
that one.
none of these are OH actually.
I know that acid tells.
So this is not an OH. This and so an aldehyde, remember, is that. So there's carbon double bonded to O and then a hydrogen. That's an aldehyde. So there's no OH on it. So there is a dipole moment, but not the hydrogen bonding kind.
So the dipole moment, like, what if there was an OH on one of them? Was
So,
that higher?
I believe that the dipole moment of acetonitrile is stronger than a single OH. If you had water, like 2 OHs, maybe that would be equivalent. But I think this one's really, really strong. I'll have to go and look it up. But so acetonitrile is like one of these solvents we use in chemistry that dissolves pretty much everything. I don't know if they still do it, but in old days, you buy acetonitrile at the drugstore, and then you mix it with a little bit of analgesic, so something like Tylenol. I mean, you would do it yourself. The pharmacist would do it for you. And then you would rub this liquid on your affected area that's hurting, and because everything dissolves acetonitrile, so I mean, everything dissolves in acetonitrile, so Tylenol would dissolve pretty well. And one of the weird things of acetonitrile is it will go into your skin, and whatever is dissolved in it will go with it. So it's a way of topically applying things to your body. It's pretty dangerous to use though, because everything will go in, whatever is dissolved in it.
Is it like on a wound or like on like a sore?
Yeah, I think in the old days they would do it with like sore joints and stuff. I don't think they prescribe stuff like that anymore though. It's probably what those pain patches now people like stick on. I think maybe there's some acetonitrile in those, or something similar.
So,
I'm not sure.
Just
Yeah.
to be clear, the higher dipole moment like overrides OH groups and like molecular
Well,
masses.
so the dipole moment is an actual measurement of how strong that difference in polarity is. So so even something that has an OH group on it, so and like this, just methane or methanol, excuse me. Yeah, this has got a partial negative, that's got a partial positive, and it's got a dipole moment that goes this way. And we could measure the dipole moment, and whatever that number is, I think it's not as big as acetonitrile. But if it is bigger, it would be a bigger number, and then that would win. But yeah, this number is a direct measurement of the strength of that how polar that bond is. So yeah, OH, NH bonds, they're going to give you really large dipole moments if they're measured. Yeah, off the top of my head, I don't think a regular alcohol beats acetonitrile, but I could be wrong. It's a special case. Okay. So, which of the following molecules would you expect to have a lower melting point?
Oh, damn it. I just realized that it's a lower melting point. That's why I got it wrong.
Oh, okay. Yeah, read carefully, please. Go back and make sure that it says low or high or whatever. So in this case, it's all about how branched it is. So straight chain alkanes are going to have the highest. So if they have the same number of carbons, the straight chain alkane will have the higher boiling point, melting point, whatever it is. Because a larger surface area, a more elongated molecule will have more interactions with other molecules. The more branched it is, the more compact it's going to be, and so the fewer interactions it can have, and so the lower the boiling point is going to be, or melting point. So this one's going to have the lower melting point since it's more branched, it's more compact. So for the same number of carbons, it's a more compact surface area than a volume. Okay. Hydrogen bonds account for which of the following observations? Hydrogen naturally exists as a diatomic molecule. So that's true, but it has nothing to do with what we're talking about. Hydrogen bonding here is not the covalent hydrogen bond. It's something else. It's an intermolecular force. B, hydrogen is easily combustible with oxygen. That again has nothing to do with intermolecular forces. That is the strength of the covalent bond between two hydrogens. Water molecules are bent or V-shaped. Well, they are, but they're not bent because of hydrogen bonding. They're bent because that's the Lewis structure, the lone pairs that they have. Air is more dense than hydrogen gas. That has nothing to do with hydrogen bonding either. So air is nitrogen N2 and it has O2 and maybe a little bit of water vapor, but it's mostly N2 and O2. There's a nonpolar. Hydrogen gas is nonpolar. It's more dense because of the weight. They're heavier. For its molar mass, water has a high boiling point. That's it. It's got a tiny mass, and so you'd expect a really low boiling point, but because it's hydrogen bonding, which is the strong kind of dipole-dipole interaction, it attracts its neighbor really well, stays a liquid. So is he. Yeah, this is the tough ones are when they're all true, but by themselves, not in the context of the question. So on a relative basis, the weaker the intermolecular forces in a substance, the greater its heat of vaporization. That's not true. So strong IMFs create things that have high heat of vaporization. High heat of vaporization means more heat is required to vaporize it. You need to add more energy to overcome those intermolecular forces. Sorry, my glasses fog up. All right. The more it deviates from, the more it deviates from ideal gas behavior. That's actually the opposite. In an ideal gas, we are assuming that the molecules have zero intermolecular forces. So the weaker those intermolecular forces, the better. The more ideal it's going to be. The greater its vapor pressure at a particular temperature. So this is a tricky one. So the more vapor it generates, that means the weaker the IMFs that hold the liquid together. So if I've got two substances and one has very weak IMFs, that one's going to vaporize very easily. That one's going to evaporate very easily. So it's going to have a large vapor pressure. So that's it, C. Because a higher melting point wouldn't make sense either. All right, you get higher melting points with stronger IMFs. So C, this is the one that goes up when IMFs go down, or vice versa. Okay. All right. The molecules in a sample of solid SO2 are attracted to each other by a combination of blank. All right. Let's start from scratch. This is a hard one. If you are not comfortable with doing Lewis structures. So SO2, to do a formal Lewis structure, you would count valence electrons first. Sulfur's got 6. Oxygen has 6 too. But there's 2 of them, so I'm going to multiply that by 2. And so there's a total of 18 valence electrons. All right, then we'll do a what do we call it? What's the term I used? A skeletal structure. So we're going to put the least electronegative element in the middle, and we're going to surround it with the other elements. It doesn't really matter how. Just put them around and connect them with 1 bond each. So I've drawn in 2 bonds. That's 4 pairs of electrons that I've already used up. So I'm going to subtract those 4 electrons from my total. And then I will do the octet rule for the surrounding atoms first. So 2 electrons next to this oxygen. It needs 6 more to have an octet. And then this oxygen needs 6 more. And now I do the octet rule for the central atom. This needs 1, 2, 3, 4. It's missing 4 to have 8. So I need 4 electrons. I've only got 2. So let's draw those 2 in. And then where am I get the other 2? That's where we share electrons from the neighboring atoms. So instead of putting them all on this oxygen, let's take these 2 and move them down here instead. And whether I took it from here or here doesn't matter. This is what resonance is, but it's not relevant to this problem. So now that we've got our Lewis structure, or a Lewis structure, we can count the number of groups around the sulfur. 1, 2, 3 groups of electrons. That's the trigonal planar electron geometry. Electron geometry, trigonal planar. And so trigonal planar kind of looks like that, right? So one of those spots is just a lone pair. The other spots are oxygens. And so you can see that it's bent. All that work just to show it's bent and not linear. If it was linear, it would be a different answer, but it's bent. And what do we know about this? Well, there's a dipole here. Oxygen's more electronegative. There's a dipole bond here. They don't point linearly, like they don't cancel each other out. They both point downwards. So there is a dipole moment in this molecule. It is polar. So it's polar, a dipole moment. And so what is holding together this thing? Everything does London forces, but it also does dipole-dipole interactions with the neighboring SO2s. Yes?
Usually, like, if you see an O in a compound, can you assume that there's a dipole moment? Like, if you see just, like, one O in a compound.
Oh, one O. Pretty much, I think.
Like, say you give
I
us,
can't think of any counterexamples, so yeah, I think so.
Like, when you give us, like, any, like, organic compound with, like, C's and H's, and there's, like, a lone O in the middle, just chilling.
Yeah, I mean, it's at least going to do dipole-dipole interactions, at the very least. But it could be hydrogen bonding, so you'll have to carefully look and see. But yeah, if it's one O, then yeah, there's going to be some kind of polar stuff happening, because oxygen's pretty electronegative.
Can we assume that for fluorine as well?
Sort of. If it's just one fluorine, yes. But if you've got 4 of them, like this, then it's nonpolar.
Yeah, like, if the number is even, then, like, probably kind of maybe it's not assumable, but...
I mean, be careful, because I think SO3, I have to draw this to make sure, but I think SO3 is trigonal planar still. And this would be, yeah, this would be nonpolar, if I'm right and it's trigonal planar. So 1O, I think you can pretty much assume it's polar. If there's more than one, just look carefully. This is not organic though. So for organic stuff, probably multiple O's, it's going to be polar no matter what. I can't imagine how it wouldn't be. but yeah. Yeah, you can take shortcuts if it's an organic compound. For inorganic stuff, you kind of have to draw it out. Make sure. Okay. So yeah, D. That was it for number 12. 13. Which one of the below liquids would you expect to have the highest vapor pressure at room temperature? You were given the following boiling point data. So this is another one where they go opposite, right? The higher the boiling point, the lower the vapor pressure is going to be at a given temperature. So remember what boiling point is. That is the point at which the vapor pressure is equal to the current atmospheric pressure. So this hits 760 torr vapor pressure at this super low temperature, whereas this only hits 760 torr vapor pressure at 100 degrees. So it goes the opposite way. The lowest boiling point is going to have the weakest IMFs, and hence the highest vapor pressure at a given temperature. So diethyl ether. Oh yeah, and there's ethylene glycol. It's even higher. It's got two OHs. And I guess the weight, the dispersion forces help it too. All right. So a liquid placed in a closed container will evaporate until equilibrium is reached. At equilibrium, which of these statements A through D is not true? The partial pressure exerted by the vapor molecules is called the vapor pressure of the liquid. Yes, that's true. Like the vapor pressure is literally the pressure of those gas particles. If there's air in there too, we ignore that part. Just the vapor pressure of water or whatever the liquid is. Liquid molecules are still evaporating. That's true too. So even though you've reached equilibrium and you measure a vapor pressure and it's rock solid at a certain pressure, it's dynamic, meaning some of those gas molecules are turning back into liquid. Some of those liquids molecules are turning into the gas at the same rate, which is why nothing looks to be changing, but it is. The number of vapor molecules remains essentially constant. Yes, I mean that's what the pressure is. It's a measure of how many particles there are. I mean you can use P equals nRT to find it. And the boundary meniscus between liquid and vapor disappears. Not true. That only happens at the supercritical, above the supercritical point, right? We've seen a video of that. There's always going to be that boundary between liquid and vapor until you get above supercritical temperature. All right, so D is untrue. The normal boiling point of liquid X is less than that of Y, which is less than that of Z. All right, so it goes X is the lowest, then Y, then Z is the highest. Which of the following is the correct order of increasing vapor pressure? So the highest, the boiling point, right here, the lower the vapor pressure is going to be. So Z is going to have the lowest vapor pressure, then Y, then X is going to be the highest. So B. Yep.
Oh wait, never mind.
Yep.
Never mind.
Okay. So B. B is it. Those are always, you gotta think twice. Make sure you get it right. Those are hard. Which of the following is the highest boiling point? So what you're doing here is you're just kind of understanding, it's a combination of what you know about IMFs and what you know about the different kinds of bonding and what kind of things that they create. So we've got a couple of molecular things, right? Ice, water, ammonia, hydrocarbon chains. These are all molecular. This is not even a molecule. This is atomic, but it's neutral. This is an ionic compound. And going back to lab 2, we've seen that ionic solids have much higher melting points than anything else. I mean, that'll apply to the boiling points as well. So chalk is going to have the highest boiling point over anything molecular, anything that has covalent bonds in it, that has distinct molecules. Another way to think about it, if you really care, is water has strong hydrogen bonding that holds, these are strong IMF forces that hold water molecules together, stronger than ammonia does, definitely stronger than hydrocarbon chains, and definitely stronger than helium gas. But those partial charges that you get can't beat full ion charges, right? So calcium is a +2, carbonate is a -2. That's much stronger than any partial charge is. Okay. Yes.
I would also like to note, I think just looking at the atoms, you can see that chalk would be the hardest thing
Yeah.
to melt.
I mean, ice is easy to melt, and
Yes.
yeah, calcium carbonate not so much.
Window cleaner evaporates on purpose. Motor oil, okay, possible.
It,
Helium's already a gas.
some people get lost in the weeds, so you need the underlying explanation too. So, but yeah. Solid iodine sublimes are the chemical forces that must be overcome. Iodine is I2. It's not a dipole. I mean, there's no, it's not a polar bond between the two iodines. It's completely nonpolar. So dispersion forces, that's it. Intramolecular covalent bonds, that's what holds the two iodines together into a I2 molecule, but you're not breaking that. You're just breaking the I2 connections, which is just dispersion forces. So C. So sublimation is solid to gas. That's it. It's a physical change. We're not chemically breaking any bonds. Okay. We have these substances arranged in, order of increasing melting point. Lowest melting substance first. The order should be what? So, this is also going to require a little bit of cross knowledge between IMFs and what we learned in Lab 2. When you look at carbon, don't think, oh, atoms. It's not just a single atom, carbon by itself, and how it would interact with other carbon. We know carbon makes really strong covalent bonds with other carbon molecules. So diamond or graphite, either one of them, has extremely high melting points. Okay, so that's going to be the highest. Probably next would be the ionic compound, calcium carbide. And then we'll go for the molecular stuff. So between CO2 and this is glucose. You don't need to really know the structure for this one. As you were saying, it's got some O's in it. It's probably polar. And this one's really polar. It's got a bunch of OH bonds in it, in addition to just regular dipoles. So that's next, and CO2 would be the lowest. So, yeah, that one's it. And honestly, just in case you weren't sure whether calcium carbide or carbon diamond or something like that comes first, this is the only one that makes sense. But refer back to Lab 2. That table in Lab 2 is a good study guide for understanding general properties. Yep.
So like an element that's alone that makes strong bonds with other ones is more likely to have a higher melting point than.
Yeah, so something that does a
carbon
covalent network. Something that does covalent networks is most likely going to have high melting point.
So I'm just I understand what you're saying, because you're saying carbon can has strong covalent networks, but why wouldn't C6H12O6 have the higher melting point? Because it has carbon in it and
So,
it's longer and it has a higher.
but so C6H12O6 makes distinct molecules, and I can't really draw it, but I think it's something like this. And there's an O in there, and then there's a carbon. There's a carbon coming out somewhere. Anyway, it's a very small molecule. I mean, it's not small, but it's relatively small. And please don't copy this because I'm probably wrong. But that's it. And then another sugar molecule would be the same molecule, but what keeps those two molecules together? They're not covalently bonded. They're going to be held together by hydrogen bonding. There's going to be a couple OHs in these things. So somewhere along here, there's OHs on here. And so hydrogen bonding is going to hold this to a neighboring glucose molecule. And that's it. So hydrogen bonding is a strong force, but it's not super strong. It's going to, I think glucose is solid at room temperature, but it's easy to melt, very easy. Whereas a covalent network, the covalent bonds just keep going. They don't stop. So that's much, much stronger. That's going to have a higher melting point. Yeah.
So, what other elements would fall with that same like covalent network thing, like silicon?
So yeah, mostly the semiconductor stuff and group 4. So group 4 elements do these diamond crystal structures.
So if there's say CaCl2 versus SiO2 up there, we're just going to have to know, because like CaCl2 is ionic, but
Yeah.
SiO2 is like a network, it's like a covalent network.
Yeah. So there's, I mean, there are a few that we've kind of gone over, and so I would, the examples that we used, that you've seen in your book, that you've seen in the workbook, I would say those are things you should know. But in general, it's going to be group 4 and a lot of the other semi-metals. So boron sometimes does covalent networks, things like that.
And
But we're not going to since we haven't talked about it, we won't touch you on it.
and so any like compound with these would be stronger than like regular ionic compounds?
I mean, there's going to be a balancing act. Sometimes you can get ionic compounds that can be stronger, higher melting points. You know, so you get really large charges but small atoms. But in general, yes, the covalent networks are stronger, harder, higher melting points. Whereas ionic compounds are a little bit more variable, a little bit less, higher. It's not as high melting point, and metals are a little bit weaker than that. Yeah, the goal is not to trick you. It's just generalizations. So stick with the stuff I think we've seen before in the problems in the books and stuff like that. All right. When a small amount of heat is added to a pure liquid, a single compound that is just starting to boil, what is the result? So the key here, if it's just starting to boil, then it's at the boiling point. If you add more heat, it's not going to go up in temperature. The extra heat that you add is going to boil more. It's going to turn more liquid into gas. So the temperature will remain the same. This is that flat spot on the heating curve. And the temperature will stay the same until it's now all gas. Yeah. So B. Okay, so we've got a phase diagram. You wish to purify a sample of X, which is collected at 1 atmosphere pressure and 100 degrees by subliming it, 100 Kelvin. And this is actually pretty common in organic chemistry. You can gently heat something at a low pressure so that you don't burn it. And at a low temperature, it'll just sublime. It'll turn into a gas. And then you've got a beaker on top that's got ice in it, and it'll collect at the bottom of the beaker, and you can scrape the crystals off. It's a nice way to purify things. So how would we sublime it? You would increase the pressure to 1.5 atmospheres, and then increase temperature to 300? No, because that's the solid region, that's the liquid region, that's the gas. That would go through the liquid. We don't want that. Increase temperature to 300, keeping it at 1 atmosphere. No, that'll still go through the liquid region. Lower to 0.5, and then increase to 200. Perfect. So D doesn't work, and E is ridiculous, so C is it. Yeah. Honestly, this is partially understanding what sublime means, because I think people can understand how to read the curve and understanding what the regions are. All right. At 25 degrees C and 1 atmosphere, X will exist as a, so 25 degrees, 1 atmosphere, there's the line. It's going to be liquid. So solid, liquid, gas. All right. The normal boiling point of X is most likely what? So we actually didn't do this with a phase diagram, but you definitely can. At 1 atmosphere, that's when we measure regular boiling points. That's what we exist under. So if we go over that 1 atmosphere line crosses around there, 48, 47, 48, something like that. There it is, 47 degrees C. That's when it's going to boil. Of course, if you lower the pressure, it's going to boil at a lower temperature, which makes sense. So there's a little bit of a vapor pressure curve on here, if you can read it, but not exactly the same thing. All right. How will the melting point of X change with increasing pressure? So as I increase the pressure, if I go up here, the melting point is going to go up. So the melting point is increasing until there's no more melting point, and we've reached a critical temperature. Okay. All right, so we've got a phase diagram again, and this is another one. So 25 degrees C, 1 atmosphere, it's another liquid, B. All right, that's an easy one. When the phase diagram for a substance has a solid liquid phase boundary line that has a negative slope. So this is not a negative slope. This is the solid liquid boundary. This is a positive slope if it's leaning that way. As what does positive slope mean? As the temperature increases, the pressure increases. But a negative slope would be going that way. And what happens in that case? Can go from solid to liquid with a small temperature range via the application of, within a small temperature range via the application of pressure. Yeah, that's true. So with a positive slope like this, if I increase the pressure, I will go from liquid to solid. But if the slope goes this way, draw it. Temperature, pressure. So let's say it's like that. If I am here, whatever that pressure, whatever that temperature is, and I increase the pressure, I suddenly go from solid to liquid. It suddenly melts. So that's what a negative slope does. It can go from solid to liquid by increasing the pressure. And that's exactly what water does. Within a small range. So you have to have a really small range of temperatures where that can happen. Yes?
You said it's a negative slope?
Yes.
Like that line?
So this solid liquid boundary, that's the negative slope here. It's as the pressure goes up, the temperature is dropping for this line.
Well, in the picture it's positive.
Well, so that's that picture, but this is a different. This is not for that question. Sorry, that's probably what the confusion is. Yeah. So that one is definitely positive.
Oh,
That's
okay,
what the
saying
question is.
one
The question is referring to a different
Okay.
diagram. Yeah. Okay. What are the other answers real quick? So sublimes rather than melts. No, because sublime is below that line. It doesn't. That's solid to gas. Cannot go from solid to liquid by application of pressure. No, that's not true. Cannot be liquefied. No, that's not true. Melt rather than sublimes under ordinary. No, that's not true either. Okay. So A is the only one that works. Choose the correct statement about the diagram here. The diagram is qualitatively correct for water. Well, I know it's not water because the solid liquid boundary here is got a positive slope. Water goes that way. The diagram shows that the melting point of the solid increases with increasing pressure. As I increase the pressure, the melting point, yeah, it does increase. So that one works. The diagram shows the triple point above 1 atmosphere. That's the triple point. It's below 1 atmosphere, so that's wrong. The diagram could represent this phase diagram of CO2. Well, this is going in the right direction, but CO2 can never be a liquid at room temperature, right? CO2 at 1 atmosphere, you would never be able to be in the liquid region. CO2 sublimes. naturally at our pressure. So 1 atmosphere would be down here for CO2. So this can't be CO2. Because dry ice just turns into a gas. So yeah, it definitely is B. Yeah, question?
Even if we like didn't know, like, or are we supposed to like kind of have an image of like what the phase diagrams look like for the common compounds?
So we talked about water. So water having the negative slope for liquid to solid. And then for the rest of them, I think you should. I mean, we've talked about CO2 as an example, and we didn't have. I don't have a demo of it, but if you've ever played with dry ice, I mean, you throw it in some water, and the reason we throw it in water is because the water increases the temperature pretty rapidly of your solid CO2, but it bubbles. It turns into a gas immediately. So CO2 doesn't make a liquid at room at regular pressures. And so, if you think about it, well, this is showing, hey, you can make a liquid of whatever the substance is at regular pressures, atmospheric pressure. So this can't be CO2. So, yeah, I would say don't memorize the specific phase diagrams, but use a little bit of common sense. If you're really not familiar with like a substance that I think you should be, ask me about it, and I can try to give you a hint. But I think most of the stuff is either something we've covered before or should be common knowledge. And if it's not, call me out on it. It's fine. Okay. The triple point of iodine is at 90 torr and 115 degrees C. This means that liquid I2 is what? So, more dense than solid I2. So, that statement requires you to know which way that liquid to solid boundary slopes. So, if this is water, water has a liquid solid boundary line that slopes negatively. And what does this mean? Well, if I increase the pressure, if I reduce the spacing between the atoms, this is showing that liquid water is more dense than solid water, ice. So we have to know information about this to gauge whether liquid I2 is more dense than solid I2. And in fact, it's not. But we don't have that information. The triple point doesn't tell us that. The triple point is just this point. So we can't really tell that A is true or not, although it's not. Cannot exist. So liquid I2 cannot exist above 115. Well, if we know where the triple point is, then yeah, that's where the liquid starts. Above that temperature and is where that liquid can exist. So that's not true. It can exist above 115 C. Cannot exist at 1 atmosphere pressure. Well, 90 torr is, 1 atmosphere pressure is 760 torr. So if you have something that's saying my triple point is at 90 torr, 90 torr, and what is this temperature? This is 115 C. So if that's the triple point, and you're at 760, which is way up here, can you have liquid? Sure. Liquid I2 definitely can exist at the high pressure. Could be anywhere in this region. Ignore where this ends. We don't know where that ends. Cannot have a vapor pressure less than 90 torr. So this is the tough one. Because we really didn't talk about how vapor pressure relates to a triple point. But what this is saying is that how do I want to explain this? Cannot have a vapor pressure less than 90 torr. Yes. So if are let's put it this way. If I this is not what I'm going to put in the exam, because we didn't really reference this at all. But basically, there is a minimum vapor pressure that substance is going to have, and it is tied to the triple point. Since the triple point of this substance, whatever it is what's iodine, is at 90 torr, then there is no way to have a vapor pressure that is less than 90 torr. This is going to be the minimum vapor pressure for this substance. Is that what I want to say? Yeah, question?
Is it because that's where they all exist? And, like, there's no other phases?
So at 90 torr, how do I want to talk about this? I mean, below 90 torr, there is no liquid at all. Like, liquid doesn't exist. It exists as either a solid or a gas. So it just can't be. I can't give you a good explanation for why at this point. Let's just skip this question, because I definitely will not put this in the exam. This is just going to make things tougher for you guys. We'll talk about the answer if we want later. I want to move on. But the correct answer is D, I think, for this one. I'll come back to that. This is not going to be in the exam, but if you're interested, we can talk about it afterwards. All right. So shown below is a phase diagram for sulfur. We have a couple different solid forms. Which of the following system is incorrect? Well, we have two triple points. Yeah, there's one there, and there's one there. That is definitely correct. You can have multiple triple points. It is basically where three different phases exist. That's all. It doesn't have to be solid, liquid, gas. Any three phases. Under atmospheric conditions, sulfur does not sublime. So there we go. Our atmospheric conditions, solid to liquid. Yeah, it doesn't sublime. It have to go solid to gas directly. So it doesn't sublime under regular pressure. Yeah.
So, sorry, this diagram is a little confusing to me. So just, is it saying like everything in the top there's the solid, like wherever there's an S is a solid?
Okay, so this is a marker, and these are markers too. The actual phase diagram lines are these curved ones. And so anything here is solid rhombic. Anything here is solid monoclinic.
Go down?
Say what?
Like, if the pressure just went down?
Yeah, if you lowered the pressure, you could get it to sublime, definitely. So if you were at this pressure and you increase the temperature, you'd be at this solid form, and then suddenly
so it's,
gas.
okay, I get what it's saying. So it's basically
But
normal. So
under-
the atmosphere is not changing at all.
Yeah, under our pressure, yeah, it would not sublime. At pressures close to 1 atmosphere, rhombic sulfur can be in stable equilibrium with liquid sulfur. So this is rhombic sulfur, and that's liquid. They do not have a boundary with each other. And so they can never be in equilibrium with each other. This can be in equilibrium with this, and then this can be in equilibrium with that, and these can be in equilibrium with the gas phases. But solid rhombus with liquid, never. They don't touch. So they cannot be in equilibrium with each other. So that's it. That's the one that's incorrect. D, at a given pressure, there is at least one temperature at which rhombic sulfur can exist in equilibrium with monoclinic sulfur. So, yeah, so at a given pressure, there is at most, one. Yeah. So this is in equilibrium with each other here, here, here. Nothing here, but yeah, anywhere in this line, they're in equilibrium. So yeah, it was C. C is incorrect. Oh, here we go. Clapeyron. The vapor pressure of a substance is measured over a range of temperatures. A plot of the natural log of vapor pressure versus the inverse of the temperature, 1 over T, produces a straight line with a slope of minus 4282.5 Kelvin. What is the enthalpy of vaporization of the substance? Okay, so, I mean, I'm just going to swap some numbers around here. So if you look at, here I'll write it just in case, the full Clausius-Clapeyron equation is this. So that's an R. And so we are plotting, like they said, natural log of vapor pressure versus 1 over T. So this is our slope. And that's why we're setting slope is equal to that. 8.314, I should have erased that one. And the slope is minus 4282.5. So solve for delta H. And basically you're going to multiply them together. 8.314 times 4282.5. The negatives cancel out. I can just ignore them. 35,604 joules per mole. And so when I convert it to kilojoules, it's going to be about 35.6 kilojoules per mole.
That's one of the answers.
It's not one of the answers, is it? So none of these. There we go, E. I hate it when that happens, but that can happen. So it's E. It's E. None of these.
Professor,
Yes.
in your key, it says D.
Oh my God. So there's a mistake somewhere then.
Oh yeah, I was super lost on
Sorry
this.
about that. I wonder if there's a typo in there somewhere. If I go backwards, let's see. So 28,000 divided by 8.314. Yeah, I have no idea. There's something's wrong somewhere. Sorry about that. I gotta remember to fix that one. There we go. I just highlighted. Okay. But yeah, it's none of those because the answer doesn't work. All right. Body temperature is about 308 Kelvin. On a cold day, what volume of air at 273 must a person with a lung capacity of 2 liters breathe in to fill the lungs? All right, this is a great gas law question because you have to think what is plugging in where. So we are talking about 2 different temperatures. We are talking about 2 different volumes. So this is Charles's law. Volume 1 and temperature 1 is equal to volume 2, temperature 2. And we have a before and after state. So we're going to be breathing in cold air. The air is going to start out cold. And we're going to breathe it in, and it's going to warm up to our body temperature. And it's going to have a volume of 2 liters. So you can set this up however you want, but that's how I'm going to interpret it. So the volume 2, this is the volume after we breathe it in, is going to be 2 liters. And the temperature of the air, once it warms up, is going to be body temperature. So the question is, well, what volume of air do we need to breathe in? And if the air is cold, it's 273 Kelvin. So that's how I interpret this. And you could have done it the opposite way. You could do the body temperature V1, T1, that's okay. But make sure that they're matched up right. So V1 is V2, T1 over T2. So I'm going to multiply both sides by T1 to move T1 to the other side. L, my units are good. The temperature's in Kelvin already. Make sure you convert any Celsius to Kelvin immediately. So 2 liters times T1, 273. over 308 Kelvin gives you V1. 2 times 273 divided by 308. 1.77 liters. So a small amount of air to fill your lungs, because as soon as that air hits your lungs, it'll expand a little bit from warming up. Make sure it makes sense. As the volume, as the temperature increases, the volume should increase too. So 1.77 goes to 2 liters. So V. Okay. All right, a sample of a gas originally at 25 C, there's C, you got to convert that, and 1 atmosphere pressure in a 2.5 liter container is allowed to expand until the pressure is 0.85 atmospheres and the temperature is 15 degrees C. The final volume of gas is whatever, blank. So let's start with the combined gas law, like the whole thing. So P1, V1 over T1, N1 is equal to P2, B2 over T2, N2. And no mention is made of changing the number of moles. So it's a sample of gas, and nothing is allowed to change. So we're going to take that out. It's the same, N1 and N2 are the same. So so pressure 1. That's the starting pressure, is 1 atmosphere. The starting volume is 2.5 liters. And the starting temperature is 25 degrees C. So we'll turn that into Kelvin. I'm going to take some shortcuts. 298. It's 273.15 is the conversion, but we don't need the 0.15 because there's no decimals. So P2 is 0.85 atmospheres. V2 is what we're calculating. And T2, 15 degrees C. So that's going to be 280, not 88, yeah, Kelvin. Okay, so we're solving for V2. If I multiply both sides by T2 over P2, notice that T2 cancels, P2 cancels. And I'm left with V2 is equal to P1 V1 T2 over T1 P2. You hate algebra, that's fine. You can plug it all in first. Simplify it, get some single numbers and then move them over if you like. But this works for me. So 1 atmosphere, volume, I'm going to leave the units off. 2.5 for the volume. T2 is 288. T1 is 298. And P2 is 0.85. So V2, 1 times 2.5 times 288 divided by 298 divided by 0.85 is 2.84. Effectively 2.8. And since the original volume was in liters, this is going to be in liters as well. So 2.8 liters. B. Okay. 32. Amount of gas that occupies 60-something liters at 31 degrees C and 367 millimeters of mercury is that many moles. So this is not a change of state. This is just, you have 3 of the properties, you want to find the 4th one. You've got the volume, you've got the temperature, you've got the pressure, you just want to find the number of moles. So that's where PV equals nRT comes in. And since we're solving for moles, we're going to divide by RT on both sides, so you get PV over RT. Well, R limits what units we can use. R is, in this case, 0.08206 liter atmospheres per mole per Kelvin. So we have to use those units. So we'll convert the temperature, obviously, that has to be done anyway. So 304 Kelvin. And then we definitely have to convert the pressure too. Our pressure needs to be in atmospheres when we use PV equals nRT. So 367 millimeters of mercury. In 1 atmosphere, there's 760 millimeters of mercury. So 367 divided by 760, 0.483 atmospheres. And now we can plug it all in. So P, 0.483. I'm going to leave the units off again. Liters, 60.82. That's actually a pretty big volume. R, 0.08206. And then T, 304. So N is going to be in moles times 60.82 divided by 0.08206 divided by 304. 1.17, 1.18 if I round it right. And there it is, A. 1 mole of gas, or about 1 mole. Okay. Um, 33. So we could do this one exactly the same as we did the last one. We can, well, not exactly, but we can sort of do it like the same way. But let's take advantage of the fact that we're doing this at STP, standard temperature and pressure. We're going to use the molar volume to solve this one. So what I want to do is find number of moles of gas. And once I find the moles, I can do mass over moles, and I'll get a molar mass. But I want to find the number of moles. So I could do this. I could plug in 1 atmosphere. I could plug in that volume. I could plug in R. I could plug in 273.15. Was that sorry? Oh, yeah. So instead, I'm going to use molar volume, and that is that 1 mole is equal to 22.42 liters. All right, the requirements is you must be at STP. So given that, if I've got 1 liter of a gas, well, I get 1 mole for every 22.42 liters. Look at that. Those cancel. 1 divided by 22.42. I have 0.0446 moles of gas. That's it. That's a nice shortcut. I don't have to use P equals nRT. And then that's the number of moles. Well, if that's the mass, 5.75 grams, I'll divide it by that number of moles. 5.75 grams is this many moles. So it must be a molar mass of 128.9. 129, if I round it right. So there's B. Okay, so focus on what you know you can do with a gas. With a gas, pressure, volume, moles, temperature. In weird circumstances, yeah, you can get density as well. But here we're finding molar mass. They've given us a mass. Well, if I had the moles, I can get molar mass, and that's what we're looking for here, moles. So it's a little bit of a tricky problem, but it's not too bad. So 34, we've got a flask. It contains a mixture of helium and neon, and the total pressure is that. There's 2 moles of helium, 5 moles of neon. The partial pressure of helium is what? So partial pressure, you can calculate it using PV equals nRT. So you plug in the moles of whatever gas you're looking at, and you can get the pressure of that gas. But you need the rest of it. You need temperature, you need the volume, and none of that's given here. So instead, we're going to use mole fraction. So the pressure of a gas A is going to be the total pressure times the mole fraction of that gas. Maybe it's backwards on the key, but whatever, same thing. So we want the partial pressure of helium. So we're going to plug in whatever the total pressure is and the mole fraction of helium. So let's get mole fraction of helium first. It's the number of moles of helium, 2.0 moles, divided by the total number of moles in that flask. So there's 7 moles, 2 plus 5. So the mole fraction is 0.286, and there's no units. Moles cancel. So the partial pressure of helium is going to be, total pressure is 2.6 atmospheres times that mole fraction. So times 2.6 is 0.74. That's the partial pressure of the helium. It's like D. All right. An ideal gas differs from a real gas in two ways. One, an ideal gas does not have IMFs, no attractions. So A. But let's look at the other ones. Have appreciable molar volumes. Well, that's the opposite. The ideal gas has 0 volume for the actual gas itself. Molecular weight of 0, that's never true. The gas particles do have mass, even if they're ideal, because that's going to affect their density, things like that. Have no kinetic energy, that's ridiculous. That's only at 0 Kelvin. It's not the ideal gas. Have an average molar mass, molecular mass. That doesn't make sense either. So it definitely is A. They don't have any attractions for one another. That's what an ideal gas does. Okay. How much left do we have? Holy crap. Let's skip a few of these, because I think some of them we've done before. So, jeez. Anybody have any specific problems they want me to do before we run out of time? Because I can skip to some of those, because we're not going to be able to finish this today. Yeah?
39.
All right, let's do 39. All right, a closed-end manometer. The fact that it's closed versus open makes a difference. So closed-end manometers, you don't have to add to the atmospheric pressure or anything like that. The difference in the height of the mercury is literally the pressure. So the difference in the mercury levels in the 2 arms was 12.2 centimeters. The atmospheric pressure was 783. The pressure of the argon in the container was what? So yeah, closed-end manometer is not connected to the atmosphere. It's connected to a vacuum on the other side. So we can ignore the atmospheric pressure in this case. So the fact that it was 12.2 centimeters means it was 122 millimeters.
What if it wasn't closed? I feel like that's gonna be on the test.
So if it's a closed-end manometer, that's the pressure. It's 122 millimeters of mercury.
Okay.
That's it. If it's an open end, then we have to add that to the pressure, the atmospheric pressure, or subtract it, depending on which way the height is.
So if you didn't have a picture, you would just have to, you not ask a question if like there's no picture provided?
So if it was an open-end manometer, there would have to be a picture to show you which way the levels are,
Okay.
or it would have to be described in the problem.
Okay.
So the height that's closest to the gas is lower, basically. And then you would know that the pressure of the gas is higher than atmospheric
Are
pressure.
you going to always be subtracting from the manometer or the atmospheric pressure? That's always going to be.
So if it's this case, so here's your open-end manometer. Okay. So if it looks like this is extreme, if that's the difference, then this is at a higher pressure. And so you would add this difference, whatever this height is, you would add that to the atmospheric pressure.
Okay.
if it was the other way, if this was higher and this was lower, then the atmospheric pressure is pushing harder. It's higher pressure. You would subtract that difference from the atmospheric pressure to get this pressure inside the flask.
Okay, so it's always going to be subtracting or adding to the atmospheric pressure.
Adding or subtracting from,
Yeah, okay.
depending on which way the height is.
Okay, right. Okay, I'm remembering it now. Yeah.
Yeah. Okay.
I was kind of confused why it came in the homework for, I think, mastery chemistry. So I was like, oh, you don't know.
You mean the open one or the closed one? Or
I think it was open.
okay. So yeah, well, open ones, yeah, you're it's a tug of war basically between the atmospheric pressure. If it's completely even, that this pressure is the same as the atmospheric pressure. So you don't, it's the same. But if this is higher pressure, then it's going to be like this. The mercury is going to go down. This one's going to go up, and this difference is the difference between the atmospheric pressure. So you add to it to get the total pressure in here. Yeah. So this one you add. If it was the other way, you subtract from the atmospheric pressure. You have another question, yeah?
Closed end versus open end. What does that really mean in terms of thermometers?
So in the open end, there's atmosphere pushing back on the other side of the mercury. In a closed end manometer, terrible drawing here. So when it's almost always going to look like this, something like that. So if there's a vacuum in here, and so there's nothing pushing back, and so the height of this mercury column is going to be entirely from the pressure inside this flask. So there's nothing pushing back, so this height of the mercury column is the pressure inside. Does that make sense? Okay. Anything else? Jump ahead? I can just start doing some random problems otherwise. Yeah.
It's not from the multiple choice, but can you do all the phase diagram problems in the short answer?
Sure.
Can you just explain really quick multiple choice before we get to?
Sure, if it's quick, yeah.
I'm just confused about 43 a little bit.
Okay. Which statement about atmospheric pressure is false? As air becomes thinner, its density decreases. I mean, that's kind of what density is. It's thinner. Air actually has weight. I wouldn't actually phrase it that way, but yes, it has mass. With an increase in altitude, the atmospheric pressure increases as well. So that one is the false one. And that's because the higher you go, the less air there is on top of you.
Okay.
And so the less force from the air pressure is on top of you, and so your atmospheric pressure is going to be lower. So if you're at the top of the mountain, it's hard to breathe, there's low pressure.
Okay.
And it's easy to think about. Think of it as an ocean of air.
Yeah, I realized after I asked when I did actually understand.
Yeah.
In question 42, it says one significant difference between liquids and gases
Uh-huh.
is that a gas, and like you said, the gas assumes the volume of the volume, not the shape.
It assumes the shape of the container too, but it takes the volume of the container. Whereas a liquid, I could half fill it and take a 2 liter. If it's half full, it's not going to have the same volume as the container.
Mm-hmm.
But gases will take the volume of the container. Yeah. Yeah.
Just some 47.
All
The
right.
boiling point.
All right.
Everything else I got, and I just had no idea. The boiling point made no sense to me.
I promise we'll get to the one you asked about. Boiling point. So to find boiling points on any vapor pressure diagram like this, you go to the definition of when does boiling occur? Boiling occurs when the vapor pressure of a liquid, so for instance, heptane, will boil when the vapor pressure, so as you're increasing the temperature, the vapor pressure is going up. More and more gas is being generated. But once the vapor pressure hits the atmospheric pressure, which is right about here, 760 millimeters of mercury, that's when the boiling point occurs. So for heptane, the boiling point is about water, about 100 degrees, similar to water. But for ethanol, at 760, that's right about here, the boiling point is about 78 degrees.
Oh, so when it reaches 76, okay, that's
Se-
right.
760. And so yeah, boiling point is always measured relative to a pressure.
Okay.
And our regular pressure for most people is 1 atmosphere. On another planet, they have different boiling points because it'd be different pressures, right? But that's how we do it. Yeah.
So if the graph reads units of like Pascal, should we look at like 101.3 Pascal?
Yes. So kilopascals, 101.3 kilopascals, or 101,300 something, 325 pascals. Yeah. But yeah, you'll get the conversions there in the conversion section. So okay, let's skip this real quick. Come back to this phase diagram for benzene. So what is the normal boiling point value? So again, normal. This is the pressure we're used to, 1 atmosphere. Well, the liquid to vapor or gas boundary is right there at 1 atmosphere. It's maybe not 80, but maybe 80. It's hard to see. Just a little bit under 80, 78, something like that. That would be the boiling point. I'll give you credit for close enough, okay? So 78 degrees C or so. What is the normal freezing point? That's, again, solid liquid. So at 1 atmosphere, freezing happens right about here. So that's not this one. Looks like just above 5.5, so 10, something like that. It's hard to read. I would give you whatever.
So A
is
is
close
like
enough.
80, 70?
Yeah, A is like 80, 78, something like that.
Right, because you said 50.
Is it in the key? It says 50?
Yeah.
Yeah, I was.
Okay. I promise I didn't write that key. I'm using something else, but I gotta fix that then. Yes.
So I was getting confused. Would it be like A where like it no longer is a liquid? Like that's what I kind of thought. Like it would be like for a freezing point. Wouldn't it have to like be where point A is, not point B?
So A is a triple point. At this point,
Mm-hmm.
you can have all 3 phases in existence.
Okay.
So, but yeah, so the boiling point and melting point, these are artificial. Like we're just saying, at the pressure we're used to, when does this stuff become the liquid?
Okay,
when
so
does it become a
it's
gas?
just whatever it's like 1 atmosphere.
Yeah, and so it's always going to be 1 atmosphere. You can make it melt. You can make it boil at any temperature you want. Well, not any, but you can make it melt and boil at lots of different temperatures by playing with the pressure.
Okay.
But so a standard boiling point is always going to be at 1 atmosphere. And which letter corresponds to the critical point? That's D. So this is why you're asking. Okay, I got to fix that key too. The triple point is A. Sublimation occurs. So sublimation is solid to vapor, solid to gas. So it's anywhere along this line. It's got to be below 0.5 atmospheres. So anything below 0.5. So 4. And the equilibrium vapor pressure of a liquid at a particular temperature is given by, you cannot get vapor pressure on a phase diagram. And that's cut, well, this is not something we talked about either. I would skip that one because we didn't talk about this. So let's skip that one.
That one just made no sense what you were asking.
There's a relationship there, but yeah, we didn't talk about it at all, so I'm not gonna go over
It
it.
didn't even seem like a question. That's where I was kind of. I didn't know what to answer at all. It wasn't a question. It would just account for the fact.
Oh, no, number 49?
Yeah.
Oh, okay. So I was talking about F, but
Oh.
so number 49. This is something we have kind of talked about. So 50 mils of ethanol and 50 mils of water. So what makes them have the volume they have? It has to be the interactions these molecules have with each other. They have to have a certain distance away to have the ideal interactions, right? So we kind of talked about how water has to be oriented a certain way
to have the most ideal interactions, right? Like this.
So is it asking why? I'm just more confused because it's not really formed as a question. That was
Okay, well, so I guess they want you to speculate.
Oh,
So,
okay.
so what would be a good reason to explain why this is happening? So the idea here is ethanol interacts with itself a certain way, water interacts with itself a certain way, and causes these ideal distances between molecules. But if you mix them together and they're slightly less than 100 milliliters, somehow the interactions between ethanol and water have changed, and the molecules can get closer to each other now. And so they're more dense together, and so the volume is going to be slightly smaller.
Okay.
I mean, this is similar to how liquid versus ice, liquid water versus ice water. Water is less dense.
Okay.
Ice is less dense. Excuse me.
So are there the questions like from the exam, but like differently worded?
Yeah, these are a little vague. But these are good for helping you kind of think about stuff you might not have thought about. But yeah, the exam that you're going to get will be very much more
User friendly.
I will make them more friendly, that's for sure. I don't like grading questions where you have to explain nebulous things like that either, because it's what is correct and what's wrong. This is more of a lab question than a test question. So,
Sorry, I think we have 49 minutes.
so it's there's no. So if the volume is becoming lower, it must mean that the water and ethanol interactions are such that they can actually get slightly closer together than the water and ethanol.
Oh,
So
okay.
somehow the way those molecules mix and the way they interact and do hydrogen bonding with each other, they can fill more of the gaps, fill more of the space. So they fit together better. And so they're going to have a slightly lower, higher density. Yeah.
As for like theory questions, sorry.
Go ahead.
As for theory questions, like, are you going to like, how many sentences are you expecting like per question? Like, I don't want to like write an essay that you don't want to read.
I mean, if you can get your point across in 2 sentences, it's perfect. The lab has the claim and evidence. That's a different thing. But for this, for the quiz, it was like, describe what's happening as you go from here to here. And all I was looking for was you start with a liquid, it turns to a solid, or it boils into a solid. That's enough. As long as you get your point across without having to make me assume you know something, then you've written enough. Okay. What else do we have here? Explain why water boils at a lower temperature versus in the mountains versus sea level. So we talked about that. Which of the following compounds would be expected to form intermolecular hydrogen bonds with water?
Is it just anything with hydrogen bonding? That's what I guess.
So,
Or is it anything,
honestly, it's anything.
is it anything that's polar?
Or is it anything with OH?
I'm not a fan of this question either, but it has to have similar strength to water's dipole moment. So water has a very strong dipole moment. If we actually had a number for it in that previous question, it would be pretty high. I think this question, if you look up the answer, it's probably only
It's all of
Give-
just the OH ones.
all the OH ones and not the dimethyl ether. So dimethyl ether has a dipole moment in it, but it's a really weak
Actually,
dipole
no, it
moment.
was dimethyl ether.
That was included as well?
Yeah, it was included. It was just
Okay.
the program was the only one not.
Oh, I didn't realize it's like multiple.
I didn't
Oh.
realize it afterwards also. It was very.
So, I mean, the idea is water does the hydrogen bonding already. So water makes a really strong polar dipole moment. That's with the hydrogen bonding part. And so that will interact with anything else that has a pretty significant dipole moment as well. So if you ever look at examples of hydrogen bonding, you'll see the OH from a water or the OH from an acid, but sometimes the OH from this acid is interacting with the C double bond O from something else. So it can interact with a dipole moment, a regular dipole as well. So if A was an answer, technically that's true, but I'm not a fan of that question. This is more of a bio problem than a chemistry one. Yeah, so I guess the question is which one of these will interact with water, most likely, and they all will except for propane. Dimethyl ether, not really though. Like it doesn't really mix with water very well. Yeah, it's not the greatest question here. This is another one of those lots of gray areas that are hard to answer.
So then what if you don't like this one?
I mean, I could put this, but I would leave off the dimethyl ether. You know, that one's a little bit.
So is the answers, Austin?
So it's all of them except for B. All of them interact with water except for B, and I would say that A barely interacts. So I'm not. That's why I would leave that one off because it's not clear. Okay. These are good ones for explain questions, and that's kinetic molecular theory. So at the molecular level, what's causing the pressure to increase when you do something, right? So if you increase the temperature, why does the pressure increase? And so you don't give me the P equals nRT answer. You tell me if the temperature is increasing, the average speed of the molecules are increasing, and if they're moving faster, there's going to be more frequent collisions with the container walls, and that's what's creating the increase in pressure. Okay? So talk about collisions. Talk about the number of collisions, the strength of the force of the collision, or impulse technically, but the force is fine. That's how you will explain kinetic molecular theory questions like that. 53. We don't have time for it, but I've got a flask. It's got these different moles, and it's got a total pressure. What's the partial pressure? Yeah, ignore that temperature because I guess you can't ignore it. So calculate the volume and then calculate the partial pressure. So how would you calculate the volume? Well, first add up all the moles, get the total number of moles, plug that into P equals nRT with pressure, with the temperature in Kelvin, and solve for volume. And then once you have that, ignore it. You can calculate the partial pressure with mole fraction. Or you can calculate the partial pressure with the moles and the volume and the temperature and stuff. There's a couple of ways to solve the last part of it. Okay, sorry we ran out of time. I'm happy to show you like how I do something if there is any problem. And if there's any other mistakes in the stupid key, email me and I can tell you whether it's right or not. I need to fix that. All right, I think we're done. But I'll stick around if you guys